For this problem, we're given the rate of increase of a population P of microorganisms at time t in hours is given by dp by dt is equal to 3p. Initially, the population was of size 8. For part A, we want to find a model for P in the form P equals A times e to the 3t, where we state the value of A. So we don't have to form our differential equation for this problem. We're actually given our differential equation. So dp by dt is equal to 3p. We are going to need to solve this though. So we can rearrange this to get the p's on its own. So you've got 1 over p dp is equal to 3 dt. As always with these differential equations, we need to integrate both sides. So we've got ln of p is equal to 3t plus our constant of integration. Well, for this form, we don't want the natural logarithm of p, we want p. So actually, we can take the exponentials of both sides and say that p is equal to e to the 3t plus c. And we're starting to form the expression that they're looking for. Well, if you remember one of our rules with exponentials, if you have two exponentials and they multiply together, you can combine them and add the powers. So actually we can reverse that rule and say that here we have e to the 3t times e to the c. Because if they're multiplying, if we add the powers, we end up with e to the 3t plus c. So p is equal to e to the c, where c is just a constant, times e to the 3t. And that is actually starting to form this expression, but we actually want a value for a, and that's where we need to read part of our problem, which says initially the population was of size 8. If we've got the initial time, that means that t is equal to 0, and when t is equal to 0, our population p is equal to 8. So we can work out what this is then. So we've got 8 is equal to, we'll leave the e to the c there. If we've got e to the 3 times 0, 3 times 0 is 0, e to the 0 is 1. So actually this constant, this e to the c, is just equal to 8. And as a is equal to our e to the c, which is equal to 8, that must be our value for a. So therefore, for our model, we've got p is equal to 8 e to the 3t, where a is equal to 8, just to clarify that. So that's part A. We can then use this to help us with some of the subsequent parts. Part B says find to the nearest 100 the size of the population at time t is equal to 2. So all this means is we have our model now, we're given a time t is equal to 2 and we just need to substitute in. So when t is equal to 2, that implies our p is equal to 8 e to the 3 times 2, which is 6, which you go to your calculator and end up with 3,227.4 and so on. But it says it wants it to the nearest 100, so we can approximate that to 3,200 to the nearest 100. So that's a nice one for a mark. Part C is going to require a little bit more work. It says find the time at which the population will be 1,000 times its starting value. So you've got to be careful with this, because it's not saying when the population will be 1,000, it's 1,000 times its starting value. In other words, as the starting size is 8, we are looking when our population is equal to 8,000. Other than that, we're going to equate this to our model. So 8,000 is equal to 8 e to the 3t. So 1000 is equal to e to the 3t. We can take natural logarithms of both sides. So 3t is the natural logarithm of 1000. T is a third times the natural logarithm of 1000, which actually we can bring that up as a power, and the cube root of 1000 is 10. So t is the natural logarithm of 10. And generally that would be okay. However, because this is a modelling problem, we actually want to write this as a time rather than just as a specific exact value. So you can go to your calculators. The time is being measured in hours, so you end up with 2.30 so on hours, and then just to tidy that up, converting it into hours and minutes, you've got 2 whole hours, the 0.30 so on, times that by 60 to get 18 minutes. 2 hours and 18 minutes. And then the final part, you can actually do without the need for getting the model correct. So even if you make a mistake somewhere in the model, you don't understand it, you can still have a go at part D. State one limitation of this model for large values of t. Well, for large values of t, according to this model, your population size is increasing, so it would continue to increase and continue to increase. So the bigger t gets, the population is going to carry on increasing forever. However, that doesn't make sense. The population can't increase forever because there has to be limitations, such as the amount of space available or the amount of food available. So something like that would be fine. So you can state that the population cannot increase forever due to limitations such as the amount of food or space available. Something like that would be fine, and they'd be quite happy. Even if you just mention that it's the amount of food that's the limitation on the amount of space, that would be fine.